All right, guys, so you can see here we're talking about the polar equation. R equals 4 times sine of theta plus 2. And they, again, same thing, want to know what interval of theta values corresponds to the inner loop. So what I wanted to show you was, what creates this limmason. So I kind of had this guy graphed over here. But if I just take that plus 2 away, you will see this guy ends up looking like a circle, right? And these were some of the examples we had done previously in this section. But as soon as I add that plus 2, you will see that's where it creates that limmason shape, right? So basically we're saying, again, we can use technology to draw the graph. The inner loop will begin and end at the origin. So obviously we're talking about right here is where the loop begins. And, of course, it's going to make its revolution go through the entire circle or that circular shape, and then come back to the origin where your R value will be 0. So they're basically saying we can solve for theta by setting our R equal to 0. So you can see in the equation, set the R value equal to 0. You get 0 equals 4 times sine of theta plus 2, move the 2 to the other side, divide by 4. That's where that -1/2 is coming from. And then, of course, you can use the unit circle or you can use the sine inverse function. But in this case, -1/2 can be found on the unit circle. So, of course, you will see we have theta value of 7 pi over 6, where sine is -1/2. And then, of course, on the other side, you will see sine is -1/2 for the angle 11 pi over 6. So you can see that's where we come up with our angles. And basically, this is telling us that, for these values of theta is where the R value will be 0, which, of course, puts us back at the origin, right? And this is where that inner loop makes this little circular motion. So the graph passes through the origin twice on the interval 0 to 2 pi, obviously not including 2 pi. So they're basically saying the inner loop, and that's, of course, the smaller little loop here, the inner loop arises from the interval, which will be between these two angles, right? 7 pi over 6 to 11 pi over 6. And you will see we are including both the endpoints, because your theta has to be 7 pi over 6 for the R value to be 0. And same thing, theta has to be 11 pi over 6 for the R value to be 0. They are also saying this corresponds to where our polar equation takes on negative values, because you can see in this case, of course, you can see part of our graph is falling below the y-axis, but they are also saying if you graph this on the r theta plane, where, theta is the horizontal axis and r is the vertical axis, you will again see between those values we have negative, right? For the R values will be negative in that case. Yeah, Phoenix, it's possible. Yeah, so you are identifying the different shapes also, but there will be some equations that will have you just, like finding the intervals and stuff that we have been doing. So you will have some examples on that also. But you will still have access to, graphing tools so that you don't have to graph by hand. You can use technology to do the graphing, but yeah, just finding the interval, you would need to solve for that. Is that kind of what you were asking? Yeah, okay. All right, thanks. All right, guys, so this was for the limmason. Now let's look at a rose. So you can see, obviously, it's not going to be very rose-like, but because it has that floral E shape to it, we're calling it a rose. So this guy is coming from the polar equation of R equals cosine 3 times theta. So just to show you the difference between the different types of equations, you will see this guy here where you just had a circle was 4 times cosine of theta, right? We kind of kept that same thing, but we added a +2 at the end in this example, which created that limmason shape. But you will notice for the rose, it's actually the theta inside your function, which is actually getting multiplied by 3, right? So you will see that's what creates the different shapes. So if we were to come back over here and let's say we did r equals, what is this guy? Cosine 3 times theta. And of course, that's the graph in the blue. So you will see that's kind of what makes a difference. If I remove that 3, you just get a simple looking circle. But as soon as I put that 3 in there, you know, being multiplied with theta, you will see that's what creates that rose shape. So same thing, they're asking us what interval of theta values describes one small loop of the graph. So of course, this guy, you will see there are 3 leaves on this rose. So again, use technology to do the graph, but then they're talking about between the interval or the interval 0 to pi yields 1 cycle of this function. They're saying, you know, again, if you look at the last problem, we can note that there is an interval on which one loop of this graph begins and ends at the origin, because just follow one of these loops. You can see we are starting at the origin, you know, we're creating this loop, and then we have to come back to the origin before you would start creating your next loop, which would also then, of course, go back to the origin before you would create that third leaf or the third loop on this. So you are always having to go to the origin. So yeah, great question, Marquise. So Marquise is asking for the rows, does it have to be any number that we multiply with theta, or does it always have to be 3? So no, Marquise, it can be any number. So, you know, we can change that to a 4 and see how that graph changes. It just creates more leaves, right? If we did 2, it will give you a different shape. So it's just about multiplying theta with the with a number, which would create the shape of, you know, whatever that rose would end up looking like. So yeah, it does not have to be only 3. It can be any number. That was a good question. 4 looks pretty cool. Yeah, it expands those numbers of leaves. So yeah, you can kind of play around with that on the Desmos graphing calculator. All right, guys. So like I said, for creating one loop, you know, we kind of start at the origin and we end back at the origin. So same thing, replace your R value with 0 in the equation. So we end up with 0 equals cosine of 3 times theta. Now, since it is 3 times theta, we'll use the U substitution here, guys. So go ahead and find the angles where cosine value would be 0. And again, this can be done using the unit circle. So you will see cosine will be 0 at the angle pi halves. And then, of course, cosine is 0 at the angle 3 pi halves. And then they are actually coming back and doing another revolution. So, you know, they're kind of starting here. We're like, okay, we go once, we come back down here, we finish a revolution, but they're going back and creating one more quarter of a circle, right? And then this guy will become 5 pi over 2 when you come back over here. And that's happening because of the, are we doing this because of the 3 leaves here? Let me check on that. So, okay, so once you find your angles over here, you know, obviously we want to undo the substitution so we can figure out what exactly theta is going to be. So wherever you had U, you would go ahead and replace that with 3 times theta. Then, of course, just divide everything by 3 and get theta by itself. So the idea here is, and that's what I was looking for. So the idea here is the reason we are going out to 3 angle measurements here is because, you know, we know that one full cycle for this function is going to be between 0 and pi. So once we clear up our theta, you will see these values will be between 0 and pi. So they're saying there are 3 solutions on that interval between 0 and pi, which correspond to the 3 times the graph returns to the origin, right? Because of the loops. But the first 2 solutions we solved are basically, they're saying, are enough to conclude where the one loop is going to be. So if you were not interested in for the entire graph and only the one loop, which is exactly what they asked us to do for one small loop of the graph, that can stay between the pi over 6 and the pi over 2. So they're saying one loop will correspond to this interval of pi sixths to pi halves. And then they're just kind of getting into a little bit more detail over here. So they're saying if we wanted to get an idea of how the computer drew this graph, we can consider our theta angle to be at 0. So you can say, okay, 3 times 0 will of course become 0 here. So you're looking at cosine of 0, which corresponds to, of course, r equals 1. So they're saying you can start the graph at 1, 0. So if you look at the graph at 1, 0, that would actually be this point right over here, guys. And then they are saying, then you can kind of go with the theta values of pi over 6 like we calculated here and pi halves. And you will see that will actually take your graph to the origin because that's where your r values are 0, right? So you end up back at the origin. And they are saying, looking at the equation, you will notice that and any angle between these two values for theta, so think about this guy halfway through there, you are going to get an r value, which is going to be negative. And you can kind of see the math over here when we change theta to pi over 3. It gives you cosine of pi. And of course, we know cosine of pi gives us -1. So they're just kind of saying that notice that with the negative r value and an angle with terminal side in the first quadrant, your corresponding Cartesian point would actually end up in the third quadrant. So you can kind of see the comparison between where your theta is, where the r value is, and the corresponding x and y values. If we put this on a rectangular plane, right? And you will see how for these angles here where your r value was negative, you are actually ending up in the third quadrant because third quadrant is where both your x and y values are negative. And so that's kind of an interesting thing that happens with this function. Oh, Phoenix, that's coming from because we know that the theta has to stay between 0 and pi. So we're kind of preemptively creating a third angle because we know once we simplify for theta, that angle will change to 5 pi over 6, which will stay within that theta interval of 0 to pi. So, if you were just looking at the unit circle, we would have gone with the first two angles. So they just kind of are working ahead of that. And they're saying, since theta needs to be between 0 and pi, they actually did 1/2 of a revolution again to take one more angle into consideration because that would be this guy over here, which also becomes 5 pi over 2. So they actually went a whole revolution and they did another quarter to come back to 5 pi over 2. And that's just because, we knew that theta has to be between these two values, 0 and pi. So they kind of did that preemptively. If we were solving this, we would probably do the first two and then recognize that, oh, there can be another one included. So it may not be a bad idea to maybe take a couple extra answers in there. And if they're not within the interval, of course, we can then discard them. And that's kind of something that will come with practice because this is very different from the different examples we have done just because polar equations work a little bit differently than our usual trig equations that we had done in the previous chapters. Alrighty, guys. So basically they are saying that since we know that r of cosine of 3 times theta is going to be negative in this interval, they're basically saying this would actually correspond to the loop, which falls into the third quadrant. So technically, this is actually the loop that we worked on. Even though I was kind of starting out with this guy, by the time we go through the math and look at the answers we came up with, it's actually this loop that we just ended up calculating for, because this is where you can see this is quadrant 3, right? Where both our x and y values are going to be negative. So as long as your theta values are between pi over 6 and pi halves, your loop on the rose shape of the polar equation is going to fall in the third quadrant. So that's kind of what they used here to show us how that happens. So as you can see, we're kind of trying to do a similar example here. They're asking us to sketch the graph of r equals sine times 2 theta or sine of 2 times theta. And of course, they're asking us to find out if this is going to be a limacon or a rose. So just looking at the equation without graphing it, what would you say? Is it a limacon or a rose? And you can type L or R if you don't want to type the whole word in there. Okay, Marquise, I see your answer. Janice, I see yours. Phoenix. Wyatt, okay, very good. Yeah, so one thing we should notice is that theta has a number being multiplied in front of it, right? Just like we saw in this example where they did cosine of 3 times theta, right? Which is what we have, sine of 2 times theta. If this was a limacon, you would have had theta by itself, but then you would have added or subtracted a number at the end of your equation. So yes, very nice, guys. This is going to be a rose. And so let's take a look at its equation. I'm actually going to go ahead and delete these. We have sine of 2 times theta, I believe. Yes. So yeah, I think Janice, you had mentioned that this was going to be a 4-leaf rose, and that's exactly what this comes out to be. And of course, you can zoom in a little bit to kind of get a closer look at that graph. Perfect, guys. Very nice. So yeah, this guy did turn out to be a rose. So yeah, just the difference between how the equation is written, and you will see how this guy ends up looking like. Now, if we were to change that, let's say to sine of theta, and then maybe did, I don't know, plus 3 at the end. So if you look at this closely enough, you will see this is not a circle, even though it has that circular shape. But if you try to find the center of this and, go out trying to do a radius, you will see this is not going to be a circle. We can kind of play around with numbers and kind of see what they look like. And you will kind of get an idea. So for this to be a rose, we have to be multiplying something in front of the theta value to get those petal kind of shapes, or leaves, I think is what they're calling it. All right, guys, so those were some of the shapes that we wanted to talk about for the polar equations. Now, the last part over here is talking about converting our equations. So you will see this one is mentioning, while many polar equations cannot be expressed nicely in the Cartesian form, or in the other direction, so vice versa, it can be beneficial to convert between the two forms when it is possible. So they're basically saying we will use the same relationships that we used when we were converting the points between the coordinate systems. So let's take a look at an example here. This guy is talking about, write the Cartesian equation x squared plus y squared equals x y as a polar equation, which would of course be with r and theta, right? So we would eliminate x and y and bring in the r and theta as our other variables. So they are saying, again, as you have seen with the other polar equations, we want to isolate the r variable when it's possible, and write r as something in the form of theta, right? So r as a function of theta. So let's start by using this relationship here, x squared plus y squared is equal to r squared. So of course you will notice that we are replacing x squared plus y squared over here with r squared, and then you're setting r squared equals to 6y. And now we can bring in these definitions here. Remember, we had x equals r times cosine theta, and then of course y equals r times sine theta. So you are going to take that y variable and basically replace it with r times sine theta. So of course you will see r squared comes down as it is, 6 comes down as it is. So it's only the y which is getting substituted with r times sine theta. And then, of course, like we said, we want to try and isolate the r variable. So we start by subtracting 6r sine theta to the left-hand side. since you have r and r common here, you will see we're taking r as a greatest common factor and factoring it out. So you end up with r times parentheses r minus 6 sine theta. And then, since this is two numbers multiplied with itself set equal to 0, that's where the zero factor property comes in. So it's either a equal to 0 or b equal to 0. So that's what we're doing. We're saying, okay, there's r by itself, set it equal to 0. There's r minus 6 sine theta, set that equal to 0. Now, of course, they move the 6 times sine of theta to the other side. And so here we're saying since r equals 0 would just be a single point, we can go ahead and reject that solution. So he's gone. And you have your conversion that we were looking for. R equals 6 times sine of theta. So this would be where we are rewriting this equation as a polar equation with r equals 6 times sine of theta. And then they're basically saying, in fact, this equation describes a circle with a bottom at the origin and a top at 0, 6. And, again, you can do a quick graph over here to check that. So this guy is r equals 6 times sine of theta. And like they said, the bottom would be at the origin, 0, 0, and its top would be at the point 0, 6, which is exactly what we have over here. So it's kind of nice to see how, now, as we said, this is not always possible, but when it is possible, it's kind of nice to see how the equations would convert between one form or the other. Okay, let's take a look at another example here. This one is talking about rewriting again the Cartesian equation y equals 3x plus 2 into a polar equation form. So here you will see we are definitely using y equals r times sine theta, x equals r times cosine theta. So everywhere that you have x and y, we would replace that. So y becomes r times sine theta. You will see the 3 and the plus 2 stay where they are, and just the x value changes to r times cosine theta. Same thing, since both of these terms have a r in it, we bring the 3r cosine theta to the left, factor out your r value, and you will see it comes out to be r on the outside, and then we are left with sine theta minus 3 times cosine theta, which we will go ahead and divide that on the other side so that we can get r by itself on the left. Again, we're always trying to isolate the r variable here, guys, and you will see this is what the equation comes out to be. So definitely looks a little bit different than any of the previous polar equations we have come up with. But, obviously, as they're saying, the polar equation is more unwieldy than the Cartesian one, but there are still times when this equation might be useful. And so yeah, so you will see this guy was a little bit of a different setup than the equation we saw before this. And the main thing on the previous example was we were able to set our equation equal to 0 over here, right? So since we were able to set it equal to 0, and when we factored it, we still had it equal to 0. That's why we used the zero factor property here. But with number 11, we kind of had the number 2 on the other side. So even when we factored it, we couldn't really use the zero factor property here because we, of course, did not have a 0 on the other side, but a 2. So the only thing we could do was get r by itself and then divide by the remaining terms. And, again, you should notice here there is no r in that sine and cosine values, right? There was only a single r that we were able to factor out. So it's a little bit of a different setup from this equation, because this one we definitely had an r square that we were working with. So just recognizing the differences between the two examples. Now we're going in the other direction. So we are given a polar equation, and you will see this is r equals 3 divided by 1 minus 2 cosine of theta. And we, of course, want to write this in the Cartesian form, which means with the x and y variables. So obviously we want to eliminate the r and theta, and we want to bring in the x and y variables. So same thing, they're saying it is usually easy to start by clearing out the fraction and then see what we can do to substitute so that, we can basically get rid of the theta angle. So let's start by clearing out the fractions, of course, reversing it, right? So since we are dividing 3 by 1 minus 2 times cosine of theta, you of course end up multiplying it on both sides. So you remove it from the right and move it to the left, and you can see we're multiplying these guys here. They are going back to this same substitution that we saw before. So since you want to get cosine by itself, we divide both sides by r. And you can see this ends up giving us cosine of theta is x over r. So that's where this guy is coming from. So they're basically saying, okay, let's take that cosine of theta function over here and replace it with x over r. And you can see this is how we eliminated the theta in this example. So now you are left with r times 1 minus 2x over r. Of course, go ahead and distribute this guy inside the parentheses. You will get r times 1, which is r. The r and r will cancel out in the second term, and you're just left with minus 2x over here. And then, of course, that 3 on the right-hand side. And then just clean this up, guys. So you will see we actually go back and introduce a square here. Once you clean this up, you get r by itself. And the reason for doing that is then we can bring in this substitution here. X squared plus y squared is equal to r squared. And you can see now this entire equation is in terms of x and y variables only. Now, obviously, this is not in the simplified form. You can see we have x on the left-hand side, we have x on the right-hand side. We have 3 plus 2x, the whole quantity squared, which obviously hasn't been simplified. But that's not what we're interested in, because we can do that later on if we wanted to break this down or not. Right now, our goal is to see, can we go from the polar equation to the Cartesian equation? And as long as you can get rid of r and theta and introduce x and y, you are good to go, whether your final answer is simplified or not. So they're basically saying when the entire equation has been changed from r and theta to x and y, we can stop unless we are asked to solve for y, or we are asked to simplify the equation further. So that's why you can see we stopped right here at this stage. They are saying if desired, the right side of the equation could be expanded. So, of course, this is where we would end up doing FOIL if we were going to expand it. And we could combine our x variables together and, like I said, simplify it if we needed to. They are telling you that this equation cannot be written as a function in the Cartesian form. Now, if you go back and think to your college algebra course and think of the function definition we had described in a college algebra course, can you tell me why this equation cannot be a function? What is stopping this equation from being a function? I mean, it's in the Cartesian form, so we do have a Cartesian equation, but why is it not a function? The vertical line test, very nice, Phoenix, yes. So the reason for that is because your y has a square on it, and whenever y has a square on it, yeah, Musa, very nice. Anytime you have not just a square, it can be any even exponent. If your y value has an even exponent on it, it's not going to be a function. And that's where it's going to fail. So yeah, like I said, you can write it as a Cartesian equation. It's just not going to be a function. Alrighty, so as you can see, they're kind of giving us examples to work through some of these conversions ourselves. So let's start out with, I'm not sure it's gonna let me copy those. So I'm actually gonna do a quick image grab over here, guys, so that I can transfer this to our board. Is it going to let me paste it? Okay. All right. So not what I was hoping it would do. Trying to see if I have an option of inserting images here. Okay, I am not seeing an option. I might have to kind of go play around with it a little bit. But let's, I guess, do it old school. Okay, so the first part is asking us to rewrite it in the polar form. So we are given y equals plus or minus square root of 3 minus x squared. So we need to write this in the polar form. So give it a thought and tell me, where would you start on this guy? And let me make this slightly bigger so you can see that better. How would we go about, because remember, this is where we need to get rid of x and y and bring in r and theta. So just to give you some of those conversions, of course, we have x squared plus y squared equals r squared. We have x equals r times cosine. And y equals r times sine theta. Okay, Jeff, you are saying square both sides. Phoenix, you went with the conversion with x and y. I actually think I like what Jeff is talking about. So let's try that first. So we would start by squaring both sides. So we would, of course, do y squared on the left. And then you've got plus or minus square root of 3 minus x squared. So if we did square on both sides here, of course, the y squared would stay as it is. And then since you are doing the entire right-hand side as squared, positive times positive becomes positive. Negative times negative becomes a positive. So those signs would actually disappear and your square and square root would cancel each other out, leaving you with 3 minus x squared. And then, of course, we can actually move that x squared, bring it on the left-hand side so that we can have x squared and y squared on the same side. So here you will notice, again, these guys cancel out. And we're left with x squared plus y squared equals 3. And then actually where you have your x squared and y squared, there we go. All right, so we can go ahead and make the substitution here, using that first conversion, x squared plus y squared equals r squared. And we can rewrite this guy as r squared equals 3. And then, of course, if we take a square root on both sides, you would end up getting r equals square root of 3. Now, if you will remember, since we talk about r as being the radius, your r value has to be greater than or equal to 0, right? So technically, when you do a square root, you get one positive and one negative root. But in this case, and we had actually seen an example like this before, you are discarding the negative answer. So that's why we're only keeping the square root of 3, the positive square root, and not worrying about the negative one. Phoenix, does that kind of make sense of why we didn't go with the cosine and sine functions and went this route? I think this would be a lot easier than going with the x and y values. Does anybody have, does anybody have any questions on this example here? Okay, so this was part A. Let's look at part B. Part B is given to us as a polar equation. So you have r equals 2 times sine of theta, and we're converting it to the Cartesian form, which means getting rid of r and theta and bringing in the x and y. Okay, so r equals 2 times sine of theta. Okay. Obviously same conversions, you know, you may just have to switch sides or whatever, or rewrite them, but the relationship is still the same between these variables. So where would we start on this guy? Anybody? R equals 2 times sine theta. We want to get rid of the r and theta and bring in x and y. So think about this example here. When we needed to eliminate theta, we used cosine theta is x over r, right? And that's what we did, was rewrote cosine theta with x over r. So that's probably where I would recommend beginning at, right? Rewriting that sine of theta so that we can eliminate theta. So that would mean, yeah, Jeff, very nice. So not just theta, but the entire function sine of theta. And then Marquise, I see yours in there. So yeah, let's take a look at that. So basically to get sine theta by itself, we would go ahead and divide both sides by r, right? So you would basically end up with sine of theta is equal to y divided by r. So that's the substitution we would do here. So replace the sine with y over r. And then, of course, we still have that 2 in the front equal to r. And then, of course, since we have a fraction, remember they also talked about get rid of any fractions that you can. So that means we would then go ahead and multiply both sides by r. There you go. So that means the r and r would cancel out here. You would be left with r squared is equal to 2y. And then, yeah, we would go back to that first conversion where you have r squared is equal to x squared plus y squared. So we can replace this guy with x squared plus y squared equal to 2y. Something is going on with my screen. It just does not want to let me write very smoothly. Alrighty, so again, as we were kind of talking in this example over here, guys, you know, if they ask us to simplify, if they ask us to solve this for y, then, you know, we would worry about breaking this down any further and simplifying it. But I think for now, we've gotten rid of r and theta. We have everything in terms of x and y. So I think I would leave it at this stage. And this is where it would be at. So just giving you guys a minute to see if anybody had any questions on part A or B for this example here. Okay, so you guys kind of saw how we went both from polar to Cartesian and from Cartesian to polar in these examples. All right, I think, is this the last example here? I think so. So let's take a look at this one here and we should be done, I believe, yeah, with 4.1. So you can see this one here is r equals sine of 2 times theta, and we want to convert it into the Cartesian form. So this one you will see, since it is 2 times theta, they are of course asking us to use the double angle identity over here, right? So we need to go ahead and simplify for sine of 2 theta first. So using that double angle identity, we replace sine of 2 times theta with 2 sine of theta, cosine of theta. And then of course, for each of the sine and cosine functions, we will bring in this substitution here. So you will see sine of theta becomes y over r. So the sine is y over r, and the cosine, of course, is going to be x over r. And so you have 2 times x, y on the numerator, r times r on the bottom. So that becomes r squared. And, of course, we would go ahead and multiply both sides by r squared so that it cancels here. R squared times r will give you r cubed. And then, of course, you're left with 2 times x and y on the right-hand side. Now, since this is a cubed function, of course, they're kind of bringing in this idea of, if you have x squared plus y squared equals r squared, and you solve it for r by itself. So, of course, you would end up with r equals square root of x squared plus y squared. So think about this. If r is raised to the third power, you raise this to the third power, which means this guy will also get raised to the third power. So that's where this terminology is coming from, because they just took this relationship, got the r by itself, and then they're saying, okay, if r is to the third power, then our right-hand side of square root will also be to the third power. And then, of course, you have 2xy on the other side. Now you can leave it in that form. You can put it in an rational exponent form. So you can see that 3 is coming from here. And again, I don't know if you guys remember this from algebra, rules of rational exponents. The denominator number tells you what the index is for your radical. So the m, of course, is your exponent, and the n is the index of your radical. So if you have 3/2 like we have here, that's telling you technically you have a square root, which is a to the third power. And you can also put, square root of a on the inside, and you can put the third power outside. So that's what they've done. Since this is a square root, they have that denominator of 2. And then 3, of course, was your exponent. So you can write it out that way. Or another algebraic form that's happening over here is if you have 3/2 over here, you can invert it and make it an exponent on the other side, and it ends up becoming 2/3. So just different forms of how you can write the same equation out. But again, guys, the main thing is to get rid of r and theta and to make sure our equation is completely in the form of x and y. So just some modifications on the same thing. So each one of these answers is basically going to be, the same equation, just written in different forms. So that is kind of, again, those skills that you gathered in college algebra is coming from. Alrighty, so like I said, that was the last example here in 4.1. And again, you have those exercises at the end if you wanted to just grab some extra practice, and you can kind of see some of those limacons, how they are kind of on the side, depending on how the equation is written out. So It's kind of neat. You can see some very different shapes that will come out of that. Alrighty, guys, let's move on to 4.2. So here you will see we're actually getting into complex numbers now. So how can we write the polar form of the equation with complex numbers? So, of course, we have talked about imaginary numbers, and we do actually talk about complex numbers in college algebra. So we're basically saying the square root of negative numbers is usually where, those imaginary numbers or complex numbers will come about. So we're basically saying complex numbers are the sum of a real number and an imaginary number. So, complex number will have a real part along with an imaginary part. And then we're talking about, so while these are useful for expressing solutions to quadratic equations, and that's exactly where we talk about imaginary numbers in college algebra, they have richer applications in electrical engineering, signal analysis, and other fields where if you guys are heading that way, you will be talking extensively about imaginary numbers. So basically, we're saying most of these advanced applications rely on properties that can arise from looking at complex numbers from the perspective of polar coordinates. So that's why we're introducing this topic to you. But again, like I said, if you guys do make into engineering courses, if that's the path you are following, you will get much, much more detail than what we are doing here. So let's begin with just a quick review for complex numbers here, guys. So remember, the basic I imaginary number, or they're calling the complex number, is defined as I equals square root of -1. Sometimes you will see they also write it as I square equals -1, because of course, if you did a square on both sides, right, you would end up with I square equals -1. So this is commonly what we call as the imaginary number. So any number that would have a multiple of I with it, so like 2I, -5I, they would all also be considered as imaginary numbers. Like, look at this example here. We're taking square root of -9. Now, again, like I said, if you take a square root of any negative number, you're going to run into imaginary numbers at that point. So what you end up actually doing is, they've kind of written this backwards over here, but I would say let's separate the negative sign from the number. So that way you can get square root of -1 times square root of 9, right? So of course, as we saw here, square root of -1 becomes I, square root of 9 is 3, and we would end up writing this as 3I. So that's your imaginary number, and you can kind of see that similar sort of breakdown over here. I just am used to writing my negative in the front, but I can see why they're doing this, so that you can see square root of 9 will come out to be 3. Square root of -1 will, of course, come out to be the imaginary number. And this is the order you write it in, guys. We would put the 3 in the front, and we would put the I in the back. So that's the notation that we follow when we're writing out imaginary numbers. Let's take a look at this definition down here. So like we were saying, a complex number is a sum of real and imaginary parts. So a complex number will actually be written in this form, A plus BI, where A and B by themselves are real numbers. But you can see A is by itself, so that definitely becomes the real part of the complex number, and the B times I, because of course there's an I on the B value, the B becomes the imaginary part of your complex number, because B has the I value multiplied into it, right? It's BI. So A is the real part, BI is the imaginary part. And again, that's the notation of how we always write complex numbers. You always put the real part in the front and the imaginary part in the back. This next part over here, you can see is talking about how we can plot a complex number. So we're basically saying if we wanted to plot, on a regular number line, if you were looking at a number 3, of course, you would start at the center of 0. You would go on the right-hand side. That's where the positive 3 is, and you would go ahead and plot it on that side. Now, how would that work for a complex number? So a complex number would have, you can see it kind of looks like our Cartesian coordinate system, but the only difference is your horizontal axis is the real axis. Your vertical axis is now going to be the imaginary axis. So you will see we're talking about, you cannot do it on a single straight horizontal number line. You would need a horizontal and a vertical axes. So like I said, the horizontal is always going to be real. The vertical is always going to be imaginary. So how would we plot a number like 3 minus 4i? So that's what we're looking at here in example 2. So let's break it down. And obviously this is going to be pretty straightforward. If you know how to graph any point in a Cartesian coordinate system, you can graph a complex number. So start by the real part. Your real part is going to be positive 3. So of course we would be doing the same thing, right? Starting at the center and going right 3 units. But now for the imaginary part, you have a negative 4i, which means you're looking at the number negative 4. So on the imaginary axis or the vertical axis, you would go down to negative 4. So you would do positive 3, negative 4, and you can see this is where we plot our complex number. So that will represent your 3 minus 4i. So just like you use your x and y axes, but just remember, horizontal is always going to be real, vertical is always going to be imaginary. And then they're just kind of getting into some of that description here, so you can kind of read through that. I guess I should ask, is there anybody who has never worked with complex numbers or imaginary numbers? Anyone who's never seen those before? Okay. I'm not seeing anything come up. Okay, so let's talk about how to do some basic calculations when you are working with complex numbers. So again, how would you add or subtract a complex number? So here you can see we're talking about adding these two. So of course we could go ahead and write it out like this. So, kind of think about what if you had, and I'm going to use the same coefficients here. So let's say if you had 3 minus 4x and you were adding that with 2 plus 5x, right? Of course, we would combine like terms, right? So the x would go with the x, the constant terms would go with the constant terms. So that's the same thing that happens here. You combine the real parts with real parts, and you combine the imaginary parts with imaginary parts. So it's literally how we do basic algebra. Is the same thing you would do with complex numbers. So as you can see, we're going to be adding positive 3 with positive 2, which ends up giving us positive 5. And then you are adding negative 4i with positive 5i. So negative 4 plus 5 will give us positive 1. So this ends up becoming positive 1i, or we just write it as I. So just again, real parts with real parts, imaginary parts with imaginary parts. And that's how you would go ahead and do that. So this guy's talking about subtracting 2 plus 5i from 3 minus 4i. So take a minute and let me see what your answers come out to be. And again, make sure when you're writing your answer, you put the real part first and then the imaginary part. Right, I'm seeing a couple answers come through. I'll give you guys just another few seconds. And let's see what your answers come out to be. Alrighty, I see Marquise. Andrew, I would ask you to check your answer. Okay, Marquise, I see your corrected answer. Phoenix, I see yours. It's been a while. Okay, not a problem. That's all right. So remember, they are saying subtract 2 plus 5i from 3 minus 4i, which means you are actually placing 3 minus 4i first. And then from that, you are subtracting 2 plus. Musab, I see your answer. All right, very good. So this would be 2 plus 5i. So of course, as we know, we need to distribute that negative sign into the second complex number. So that would actually come out to be, of course, your first one will stay the same. All right, Andrew, I see your corrected answer. So yeah, 3 minus 4i will stay the same. The negative will make the 2 into a negative number, so he becomes negative 2. And the negative will also make 5i into a negative number, so that becomes minus 5i. So yeah, combining the real parts, you have 3 minus 2. And then combining the imaginary parts, we have negative 4i and negative 5i. So as you can see, 3 minus 2 gives you 1. Negative 4 minus 5 will give us negative 9. So that ends up becoming 1 minus 9i. And I think all of you who shared your answer with me did reach that conclusion, didn't you? All right, those of you who did not get the correct answer, do you see what happened, where the error happened? Okay. Does anybody have questions on this guy? So like I said, if in your mind, it helps to think about the I as, your X variable, try it that way till you get comfortable working with the imaginary numbers. All righty, very cool. Now we're getting into some basic other operations. So you can see we're now doing multiplication and division. So as you can imagine, same thing like we did with algebra, you will go ahead and distribute that 4 inside the parentheses. So as you can see, 4 times 2 will give us 8. 4 times 5i, 4 times 5 is of course 20. So that will end up becoming 20i, right? So just use the distribution property to figure that guy out. Now in example 5, again, you can see there are two complex numbers being multiplied. So 2 minus 3i being multiplied with 1 plus 4i. So you will see again, we're using our basic FOIL techniques over here. So we do 2 times 1, which of course will give us 2. We do 2 times 4i, so that will be 2 times 4 is 8, so that becomes 8i. Then you do negative 3i times 1, which will of course be negative 3i. And then negative 3i times positive 4i. Negative times positive is negative. 3 times 4 is 12. And then, of course, I times I becomes I squared. So you will see this guy here becomes minus 12i squared. However, remember how I showed you at the beginning, we can rewrite I squared as negative 1. Now, you will have to do this here, guys. If you are multiplying complex numbers and we do a FOIL like we did here and you end up with I squared, replace that I squared with negative 1 because then you will see this sign here changes. Negative times negative will end up becoming positive. So you end up with 2 plus 8i minus 3i, and that term at the end would become positive 12. So you will see when we combine real parts, this now has turned into a real number. So it's 2 plus 12, which is where the 14 comes from. And then 8 minus 3i gives us 5i, and that's where that 5i is coming from. So this little conversion here is very important to remember that I squared will become negative 1. Okay. So that's with multiplication. Now, let's look at division here. So division, again, you can see we're taking two complex numbers and dividing it by each other. So you've got 2 plus 5i being divided by 4 minus i. And they're basically saying to divide two complex numbers. We devise a way to write this as a complex number with the real part and an imaginary part. So, of course, we want to separate the real from the imaginary. So the first thing you want to do is eliminate the denominator. So what you end up doing, it's kind of the same thing we did, which again, we haven't really had to do that in trig so far, but remember when we talk about rationalizing the denominator and we multiply by the conjugate of our denominator, you're actually using that same property here, but since we're working with complex numbers, you are multiplying by the complex conjugate, which means what? If this guy is 4 minus I, its complex conjugate is going to be 4 plus I, because remember, by changing the sign between the two binomial terms, you create its conjugate. Since these are complex numbers, you end up with complex conjugates. And again, the property that we're using here is, remember, when you have two conjugates that are being multiplied, they end up becoming a square minus b square. So in this case, what will happen is, let me show you. So, of course, the numerator, we would need to go ahead and multiply. Gonna try and see if I can keep that whole thing on my screen so you guys can kind of see the transition happening. Okay, so of course, on the numerator, where you have 2 plus 5i multiplied with 4 plus I, you will of course see we are doing FOIL here again. So go ahead and multiply that. Same thing, make sure you replace your I square with -1. And then go ahead and simplify it. So that's your numerator. On the denominator, we will be applying this multiplication idea here, which they did kind of go ahead and show you by using the FOIL method. But honestly, you do not have to do the entire math over there. So if you have 4 plus I being multiplied with 4 minus I, using this idea of a squared minus b squared, this will end up becoming 4 squared, which of course is 16, and then minus, we would do I squared, which again, if you think about it, using this same rule over here, I squared is -1, which will end up becoming 16 plus 1, and you will see that guy ends up becoming 17. So you no longer have complex numbers on your denominator. It just becomes a real number of 17. So this is why we multiply with the complex conjugate. So if you have 4 minus I on the denominator, multiply your fraction by its complex conjugate, 4 plus I, and you have gotten rid of the complex number on your denominator. And now we can go ahead and do, just a basic simplification over here. And you will see now, and I know I cannot keep both of those pages anymore since I do need to show you this part here. So what's happening over here now, you have 3 plus 22i on the top and just 17 on the bottom, right? Like you can see here. So now you separate the real part. So you take 3 over 17, and then you separate the imaginary part, and you get 22i over 17. Now, if you could reduce the fractions 3 over 17, you would. If you can reduce 22 over 17, you would. So you want to separate those. So remember that 17 applies to everything on the numerator. So each of those values is going to get a denominator of 17. And this is still a complex number. This becomes your real part, and this becomes the imaginary part. So basically, the idea is, guys, do not leave a common denominator like the left-hand side here. Do not leave it in this form. Make sure you are breaking it down into two separate fractions. So question on multiplication or division of complex numbers? Okay, take a minute. Let me know if you have any questions. And in the meantime, let's go ahead and try and set up our try it now. So of course, this guy is going back to multiplication here. So let's see, we are doing 3 minus 4i multiplied with 2 plus 3i. So of course, you are using FOIL to break this down. So take a minute, go through that math, and let me see what your answer comes out to be when you multiply these guys. All right, Marquise, I see your answer there. Very good. Musab. Okay, you have a different answer than Marquise. Okay, Jeff, I see your answer in there. Andrew. All right, so let's see what's going on. All right, so of course, since we're talking about FOIL, you multiply the first terms, the outer terms, the inner terms, and the last terms here. So you are doing 3 times 2, which will of course be 6. 3 times 3i would be positive 9i. And then let's see, negative 4i times 2, so that would be what? Negative 8i. And then negative times positive would be negative 4i times 3i. 4 3s are 12. And of course, you would have I squared, right? All right, Phoenix, Janice, I see your answers in there. So 6 plus, well, I'm actually going to go ahead and combine these two here. So 9i minus 8i will, of course, become 1i, right? 9 minus 8 is 1. And then over here, minus 12. Again, remember, you have to use that conversion. I square is negative 1. So we replace our I square with negative 1, which ends up making this 6 plus I, negative and negative will become positive. So that becomes positive 12. And then we can combine positive 6 with positive 12. So you will see this comes out to be 18i when you multiply these two. So those of you who did not have the correct answer, please make sure you go and see where the error happened so you know, oh, this is what I did wrong and I want to be careful about that. Questions on this one here, guys? Okay, so we have just gotten started in this section. You know, obviously we're still just kind of reviewing complex numbers at this point, but now, as you can see, we will get ready to talk about how to use complex numbers in polar form. So that's where we'll be heading next. This guy over here is just kind of talking about you know, with the interpretation of complex numbers as points in a plane, you can basically use that same idea of, you know, the Cartesian coordinate system. So obviously, as you can imagine, if we are talking about these points by its horizontal and vertical coordinates, you know, using its polar location, we would be talking in terms of origin and the angle, right? So you would see a little bit of overlap between the discussion we've had so far in 4.1, and we'll be kind of building up on that as we're converting these into polar form. So we'll kind of pick up from there, guys. We're already at 11. So if you have any questions, I'm happy to stay back and answer any of them. Now, remember, today is the only class we are having since Wednesday onwards. We have Thanksgiving break. So there are only classes today and tomorrow, and then college is closed starting Wednesday. So we will actually be back next Monday. So let me know if you have any questions in the meantime. All right, guys, take care. Enjoy your holiday break. Take care, everyone. Be careful and see you next week. Bye, guys. Take care.